Hello, and welcome back to Recitation. Here on, not where we originally told you it was going to be, but here on Twitch. I'm Jacob, I'm going to be your TA. The first thing I need to do tonight is I need to correct a very large mistake I made last week. I forgot to credit our wonderful TA, Ivan, who made a lot of the materials a lot of the really cool stuff you've been seeing. He made that thumbnail that you might have seen if you checked out the videos on Canvas or if you went to the Microsoft Stream link we sent out this morning. He made this layout you see right here. He made that starting student screen. So I need to give a huge shout out to him. I can't believe I forgot that last week. That's my bad. As to why we're here, conveniently, Microsoft Stream, despite working last week, this weekend when we tested it, it decided to go down right as I tried to start streaming to it. So this is our backup, because BlueJeans is having issues too. So this is really all we could go to. We're probably going to try to move back to Microsoft Stream next week, but who knows what's going to work at this point. Regardless, you can see what we're going to talk about today. Brute force, Boyer-Moore, and Knuth-Morris-Pratt. Those are some pattern matching or string searching algorithms. We'll get to those in a second. For now, I have some announcements I want to give people a little bit of time to trickle in, because this was a very last-minute change of location. Even in distance learning, we can have change of location. First of all, I'd like to remind people about the process for asking questions. Remember that you are making posts on Piazza to ask questions that will get forwarded to me. I'll see them and answer them on stream. So please don't try to answer questions or to ask questions on stream somehow through Twitch. It won't work. Please go through Piazza. Something I recommend, and I mentioned it in the announcement, is make like a template question post on Piazza. So just start making a question and then fill out like the title thing, put it in the right folder, make it private, etc. So that if you have a question during recitation, you just need to actually type in the question and hit send. You don't need to do all of the rest of it. That might make it a little bit faster. We'll see how that goes. Another thing I wanted to mention is don't forget that TAs and Dr. HB do still have office hours that you can schedule via BlueJeans. So you just need to email your TA, or email whatever TA you want to schedule a meeting with, or email Dr. HB and you can schedule a BlueJeans conference to talk to them via webcam and get to ask them questions and get some feedback. Another thing I want to mention that you've probably seen the couple announcements we've sent out is the TA application is open. That's available at ta-app.cc.gatech.edu. You can apply to be a TA for CS 1332 or your favorite inferior class. Up to you. Sorry. But it is open. We are accepting applications. For 1332, you need to apply before the end of the day, Friday. That is when we're going to start making our cutoffs. So please apply by then. It's that link right up here. You need to be on the campus VPN to do it. So most people aren't on campus right now, so you aren't inherently on the campus network. You'll either have to download the VPN, and I've linked instructions about that on the announcement, or something that you're able to do is you can go to vpn.gatech.edu and access it through there. I haven't really used that site too much, so I can't verify exactly how great it is going to be, but it should work. You might need to refresh your page after logging in. The couple times I've used it, I've had to refresh my page for it to actually work, otherwise it starts loading forever. But somehow be on the VPN, access that site, and apply to be a TA before the end of the day Friday. Email your recitation TAs if you have questions about the process or questions about what the responsibilities of being a TA are. Some other stuff, just normal announcements about homework. Your homework 8 was due yesterday. There were some issues people had with time zones, so we decided to end up ignoring late penalties for that one, but make sure you're aware of your time zone for the future homeworks. They're due at 11:55 Eastern Daylight Time, not whatever time zone you might happen to be in if you're in a different place. Please make sure you get them turned in on time for homeworks 9 and 10. Homework 9 is due relatively soon. I believe it's this Friday. I have that written down somewhere. Next month, Monday, April 6th. That's when string searching is due. Graphs homework that was already released, that's going to be due on April 13th, so the week after string searching is due. And those are your last two homeworks. Homework 10 is the final homework of the semester. Nothing else to worry about after that. We just kind of released all the stuff early, just so you have even more time to work on them. Graphs won't be on exam 3 or anything, so feel free to delay on that, working on that if you want to for a little bit. So we're going to be covering Homework 9 content and recitation today. Other important stuff is you've got your exam coming up. It's a week from tomorrow. I'll be releasing a topic list about that tomorrow so that you can get an idea of what's going to be on it. I'm not going to say too much about that as isn't already said in the announcement because I don't want to accidentally say anything wrong, but check the announcement that we've sent out. There's a ton of information about it. A lot of stuff's changing with that, and we can try to answer your questions on Piazza or via email. Next, I wanted to thank everyone who filled out the survey form we sent out after last week's recitation. I did go and read all of the responses that you guys sent to that, and I'm going to try to incorporate what I can. Some of the common ones I saw was, and this one's my fault entirely, is that my webcam would sometimes go out of focus on that board sometimes, so that's entirely my fault. I've disabled all of the autofocus and auto calibration features on it, so I've manually tuned it to get a pretty good shot of the board, so hopefully it will stay in focus the entire time and it shouldn't change at all. Another really common comment I saw was just because I have all the stuff a lot of the stuff is kind of written on the board already, people weren't necessarily having enough time to write everything because they're trying to catch up to what's already written plus what I'm currently talking about. So Landon and I did talk about that a lot this weekend, and kind of the decision, well, my decision, both of our decisions, I can explain kind of my reasons for it, is for those that don't really know me that well, my handwriting isn't very great. So if I'm trying to write everything down live, a lot of the stuff might be really hard to read, and that's not very good when it's kind of inconvenient to keep asking questions. And another thing is I'm working with very limited space on this board. I don't have kind of a huge whiteboard to write stuff on. So I need to plan out generally like where things are going to go and like what papers I'm going to use, where stuff's going to get put. Otherwise I risk running out of space, and that's going to make things look really ugly. So I'm going to keep having the stuff pre-written, as you can tell, but what I will try to do is I'll try to give you guys a lot more time to actually write down stuff before I kind of write down even more and give you guys more stuff to catch up on. Unfortunately, if we were on Microsoft Stream, you are able to a little bit better pause the stream there, and it doesn't force you to go back up to live. You can resume it from where you paused. Twitch is a little bit worse in that respect, but hopefully I'll try to make it a little bit better for you guys this week. It was a very common thing, and I'll try to do what I can. Some other things you guys mentioned were about trying to maybe incorporate some kind of live involvement, like a Kahoot or something, and we'll look into what we can do for that for the coming weeks. If we use Microsoft Stream, it's got a little more delay, so it can be a little bit harder to do something like that. We'll see what we can work with. Other stuff about trying to make the Q&A stuff easier using like other Q&A platforms. The issue is a lot of the other platforms, especially ones you guys suggested, we've looked into a lot of things, and a lot of things don't really work the way we want it to. Stuff like BlueJeans and WebEx doesn't really play nicely with the software we're using to stream. You can tell we're not just using like a normal screen share. We kind of have multiple webcams, a whole layout going on. So not everything works perfectly with that. Stuff we've checked out, like the Piazza's live Q&A feature that they recently rolled out, and that doesn't really work exactly how we want it to. So we'll stick with where we're going for now. We might try new things in the future, see what we can get working, but we just have a lot of criteria we need these things to meet, and if they don't meet all of them, it's not really good for us. And kind of the last thing I saw mentioned a lot were people asking if I could kind of cover stuff that's a little more specific to the homework. Instead of last week, I talked about a lot of vague diagramming stuff. That was mostly because the stuff I covered last week wasn't on your homework. A lot of it wasn't. That's why I was a little vaguer with it. This week you'll see I go a little bit more in depth into how the algorithm stuff works, and hopefully that will be a little bit better for you guys. With that said, as usual, ask your questions when you have them in chat. Don't necessarily wait for me. I'm going to go ahead and get started with pattern matching today. Ooh. It's not ideal. Alright, that looks a bit better. Okay, pattern matching. What is it? It's the focus of this homework. Sometimes we might call it string searching instead of pattern matching. I want to say that they're exactly the same thing. Don't worry about like, oh, string searching is one thing, pattern matching is another. They're the same thing, don't worry about it. What our goal in pattern matching is that we have some pattern that's a short text, maybe like a word or a name, or like a single like line of code that we're looking for, and we're looking for it in some larger text that might be like an entire text file, maybe like one of your homework files. Maybe it's like a book that you're searching through. And our goal is, we have one of kind of two objectives. We're either trying to find the first place the pattern appears in the text, or we're trying to find all places the pattern appears in the text. So say that this entire board was my text and my pattern was the word of. Well, I would search through all of this for every time the word of appears. So if I was looking for the first occurrence, that I believe would be right here. If I was looking for all occurrences, you'd get a couple more. There's one here, one here, one here, one here, etc. And a little bit of notation I'm going to be using for a lot of today is m is going to represent the length of my pattern, and n is going to represent the length of my text. So in that example I just said, m would be 2, because of is 2 letters long, and n would be the length of this entire, like all of this text here. So n is generally a lot bigger than m, and you can pretty much always assume n is at least as long as m, because we can't find, like, if my pattern was the entire, like, dictionary, that's obviously not going to fit on this board, so there's no possibility that a longer pattern exists in a shorter text. So with that said, let's get into how we actually accomplish this in code. There's a bunch of techniques we can use. We'll start kind of with the simple one, and then we'll move on to some more advanced stuff. First algorithm we're going to talk about is called brute force searching. So as the name suggests, this doesn't really have any kind of optimizations on it, nothing special or fancy at all. We're just a basic search straight through the entire text to find what we're looking for. So I'm also going to introduce some other notation that I'm going to try to keep constant for all of the pattern matching algorithms we talk about today, but there are other ways to use pointers in your code during this. A lot of, like, the pseudocode we give, some of it does a little bit differently. It's the same algorithm, there's just multiple ways to kind of write out what your variables are going to be called. But the way I'm going to try to keep consistent throughout today so that your code kind of can be consistent within itself. I is going to be a variable that represents the start of the text in my current alignment. And that will make more sense once I actually write down some examples and show you what it looks like. But I is always going to be the kind of where the first character in my pattern aligns with my text. So when I get a complete match, I points to where that match happened. That's going to be very useful for returning things. J is going to be the current index I am in my pattern. So if I'm comparing the first character in my pattern, J is at 0. If I'm comparing the third character in my pattern, J is at 2, etc. So J is going to be moving kind of a lot more than I, it seems like. In terms of bounds, I can be anywhere from 0 to essentially the end of our text. You'll see I say n minus m here, and that's because once the pattern extends past the length of the text, it's not possible for there to be a match anymore. So there's no point for us to keep looking. Say, like, the word brute force was my text, and the word I'm looking for is, like, onomatopoeia, really long word. Once I get to, like, I being at F, the word onomatopoeia goes way past the end of my text. It's not possible, no matter what the characters are, for there to be a match there. So I shouldn't even try to do comparisons. And again, you'll see what that looks like in the examples we talk about, but that's where this n minus m is coming from. And since j is an index in my pattern, it's only ever between 0 and m. Remember, m is the length of my pattern, n is the length of my text. How all of these algorithms work is we kind of need to define 4 things. What do we set our I and j at when we start? What do we do when a single character matches? What do we do when a single character mismatches? And what do we do when we found a complete match? Assuming that we're trying to find all the occurrences. If we're trying to find a single occurrence, then a complete match just means we return. But if we're trying to find all of the occurrences, then a complete match means we need to keep going. How do we do that? That's going to be algorithm dependent. So, how does this look like for brute force? Well, we start with I and j just at 0. That means we're starting at the very beginning of our text and the very beginning of our pattern. If we get a character match, we increment j, and incrementing j means we're at the next character in our pattern. If we get a character mismatch, what we're going to do is increment I. Incrementing I means we're done with that alignment of the text and pattern. It didn't work out. incrementing I means we're just moving one spot forward, and I reset j back to 0. Same place we started with. That just means I'm going to start over at the beginning of my pattern again, not going to use any kind of information I've gained at all. If I get a complete match, I'm going to do the exact same thing. So complete match, there's nothing we can take advantage of. We just shift the pattern over by 1 and reset j back to 0. And this is a point I mentioned earlier. If I goes past n minus m, so if the pattern goes past the text, we have to stop. That's not necessarily explicitly stated in every algorithm, but it's very important, and if you've started working on your homework, a lot of people have run into issues with that. If there's no longer a possibility that you get a match at all, then you should stop your algorithm. Hopefully everyone's had time to write this down and get an idea of it. Let's see what it actually looks like in practice with an example pattern, an example text. So, this is the text we're going to be running through, go gob ghost. The pattern we're going to be using in this case is ghost. So we can see just by looking at it that we have this alignment here. That's index 0, 1, 2, 3, 4, 5. Index 6. So that should be where we find our match. So let's try to run through this using brute force and see what happens. So the first thing we do is we start at the very beginning of our pattern. I've got my I and j pointers just like last time. I is going to start at index 0, and j is going to start at index 0. We're going to compare. Now, how do we actually do the character comparison? Because I is not moving, j is the only thing that's moving. How we get the spot to do our comparison is we compare j in our pattern with I plus j in our text. And that'll make a little more sense once I start moving this, but you can see when they're both at 0, 0 plus 0 is 0, so I get the beginning of my text with the beginning of my pattern. They match. I'm going to represent a match just by circling the letter to indicate that we got a match. And then I increment j. Now in this case, I'm comparing index 1 of my pattern with index 0 plus 1 of my text. That's these two h's, that's where they align. That's a match, so I increment j. Again, I get a match here. It's index 2 of my pattern and index 2 of my text. Now here I'm going to get a mismatch, and I'll draw a circle and then cross it out to indicate that that was a mismatch. So, what do I do if I got a mismatch? If we remember from the previous slide, I just increment I by 1, and I reset j back to 0. Now where I'm going to put j, I'm not going to necessarily keep j at the beginning. J is always an index relative to our pattern. So I means our pattern aligns here, which means I should write out the word like this. And if j is at index 0 of our pattern, then that's essentially going to be right here. So in a lot of diagramming examples, we write the pointers like this. This is essentially I is just kind of where we started with our pattern alignment, and j is going to represent the column we're currently comparing. And that's how these diagramming examples generally tend to work. But here, I is at 1 and j is at 0, which means we compare the 0th index of our pattern with the 0 plus 1 index of our text. That's this h and this g, and obviously those don't match. So, just like before, we increment I, and now we realign our pattern. And j is going to start here again at the beginning of our pattern. O and g get compared. Obviously, they don't match. And now we're here. That's I at 3, j again, still at 0, even though it's kind of shifted from the beginning. We start comparing. We get a match. J is going to move forward by 1. So now we're comparing in terms of like the pointer math. That's index 3 plus 1, which is 4 of our text. That's I plus j, with index 1, which is this h of our pattern. And that's where we get a mismatch. I know I'm stressing this pointer math a lot. I'm going to stress it a little bit less on the other two algorithms. I just want to explain that it can look a little weird when I'm diagramming it because it's not necessarily the same way it feels in code, even though it does work that way. So we got a mismatch, which means we realign our I, and j gets reset back to the beginning of our pattern. We get another mismatch here, and we increment I. B and G mismatch, so we increment I. And then now we do our comparisons. G matches, so we increment J. H matches, O matches, S matches, and T matches. So that's a complete match. So we could store this index to return or return it depending on whether we were looking for one occurrence or all occurrences. I is at index 6 right now because that's the start of the alignment, so that's the index we can look at to return. Now, if I was going to keep looking for all occurrences, the next thing I would do, based on the algorithm we talked about, is I would move I forward by 1. I would remake this alignment. But now you'll see something interesting. This T doesn't match up with any character in our text. The pattern's kind of hanging off the edge. And that's when I is greater than n minus m here. That's that exact case I talked about before. So because there's no possible way this could line up, because this isn't a character, there's nothing it could possibly match with. We don't do any comparisons here. So there's no circles, I don't check the G. No comparisons happen here, we stop immediately. And this could definitely be a place where you get like one extra comparison if you check this G, or a couple if you check these next few characters. So make sure that that's a termination condition you have. If you extend past the end of your text, you should stop immediately. This means that if in one of the future algorithms we're talking about, if your pattern is longer than your text, you shouldn't do any work at all. There's no possible way you could have any matches. All right, I'm going to talk about the efficiency. Feel free to submit any questions you might have. I'll be looking at those, but I'm going to start talking a little bit about the efficiency. I'll put aside these I and J pointers because we will need them later. So let's start with the worst case of brute force. The worst case for brute force is if I start comparing, get all successes all the way down to the very last character, and then I fail. Then I shift the pattern forward by 1. I get successes all the way down to the last character and fail. So how can I do this? Well, if my pattern is like, this is seeable. If my pattern is like A, B, and my text is all A's, then that exact case is going to happen. And the number of total comparisons I'll have to do is the length of my pattern times the length of my text. Because for every alignment I check the entire length of the pattern. And remember, since we called those n and m, that's going to give us a worst case time complexity of O of m times n. That's our worst case. Now what about our best case? I gave myself a lot of room here, and that's because for a lot of these algorithms there isn't really one single best case. Now for the best case, we are going to ignore that case I mentioned earlier, where if your pattern is longer than your text, you don't do anything. That's kind of a really trivial case, so we're going to ignore it. But my best case does depend on whether I'm looking for one occurrence or all occurrences. If I'm looking for one occurrence, then my best case is that I find a match at the very first alignment I do. So the beginning of this text is ghost, match ghost immediately, I'm done. That's all I need to do. In that case, all it takes is one iteration over the pattern, and since the pattern is length m, that's going to give us a best case of O of m for one occurrence. But what if I'm looking for all occurrences? Well, in all occurrences, that would be just like our worst case was AAAB, our best case would be something like BAAA. Again, looking through a text of all A's. I'll kind of mark which one is which. That one specifically. If I'm looking through a text of all A's and my first character is a B, every single alignment I'm going to mismatch on the first character. So I'm just going to kind of do all of these shifts by one comparison each. And since that's going to go across the entire length of my text, that's going to give me O of n time, because n is the length of our text. So our best case is O of m for 1 and O of n for all. We would always be very specific on a test if we were asking like what the best case of brute force is. We would ask whether we meant one occurrence or all occurrences. Average case, you shouldn't really be surprised by this, but this isn't a great algorithm, and our average case isn't really going to be better than our worst case. You see, we did a ton of comparisons here. Even when we generally failed on the first character, we still did a lot of extra comparisons. You can see like right here, did a lot of failed comparisons. And our worst case is going to, or our average case is going to end up being the same as our worst case, O of m times n. Now, I'll give you guys a little bit to ask some questions, but then I'm going to move on to the next pattern matching algorithm we're going to talk about, where we're going to improve on brute force by doing a little bit of pre-processing and optimization, and we're going to see what better time complexities we can get from that. I see one question being typed out. My camera has gone out of focus. It does not look like that for me. And it looks fine on the stream. I can try to adjust it, but honestly, it does look fine to me. I don't know if it was strange for a second. I don't want to mess with it too much while the stream is live, and I'm having other people say it's in focus for them. So I think I'm going to leave it. Okay, I now have 2 people saying it's in focus and 2 people saying it's out of focus. Question, why would we not move I to J after finding a match? Well, imagine we have a pattern like a ton of A's in our pattern and a ton of A's in our text. In that case, we have a match at every single possible index. So we have a match at 0, a match at 1, a match at 2. If we shift I all the way past J, then we miss all of those matches in between. Yeah, make sure that it might just be the quality of your stream that's low, so make sure that's not an issue for your focus. But yeah, we can't shift all the way past that because we might be skipping matches in between. Great question. Another question, what if we have a pattern that's the exact reverse of the text? Wouldn't the worst case of brute force be O of m? That wouldn't be... I mean, that wouldn't be our worst case, because our worst case is worse than... our worst case is m times n, which is worse than O of m. You are correct that if the pattern is the exact reverse of the text, it really depends on the pattern. Like, if our pattern is all A's followed by a B, and our text is a B followed by all A's, then we mismatch immediately, and it's kind of an O of 1 comparison. But I would not call that our worst case, no. Great questions, though. All right. I'm going to go ahead and move on to Boyer-Moore, I think. Go ahead and mark that off. Looks like my camera like blue tinted a little bit in the background. I don't know how to feel about that, but the board generally looks fine to me still. I'm going to keep going. All right, Boyer-Moore. This is the next algorithm we're going to talk about. This is how we're going to improve on brute force. So one of the ways we're going to improve on brute force. We're going to do that by pre-processing the pattern. What that means is before the algorithm even starts, we're going to do kind of one loop over the pattern, do some work on that in order to give us information we can use during the algorithm, that we don't just have to do all of these shifts by 1 every single time. Because obviously that's a really big issue in our algorithm. If we're constantly shifting over by 1, we're not really going to get really good efficiency. So, how Boyer-Moore works is every time we fail a comparison, note I underlined fail specifically because you'll see a difference later. When we fail a comparison, we look at the character in the text that we failed with. So, for example, I'm going to go back to the brute force example here. What I mean is, for example, when we failed at this comparison, we're going to look at this G. That's the character in the text we failed with. And that's going to be what we use in Boyer-Moore. And by looking at those characters in the text, this is going to allow us to skip alignments where a match is impossible. What do I mean by an impossible match? Well, if my pattern is all A's and I encounter a B in my text, no alignment that includes that B can possibly match with my pattern, because my pattern doesn't have a single B in it. So we can kind of use these characters to figure out what alignments aren't possible. And how we do that in code is what's called a last occurrence table. What a last occurrence table does is it's going to map every, so it's just a hash map. It maps every character in the pattern to the index it last appears in the pattern. I'll build an example of that in a second, but I'll just repeat this. For every character that's in the pattern, it maps to a number, and that number is the last index it appears in. So if it appears one time, it's just the index of that character. If it appears multiple times, it's the index of the last time it appears in the pattern. And then for every character that's not in the pattern, it's going to map it to the number -1. Now, how we actually implement this is a little bit different. Why is the best case not O of m plus n? Don't we have to make m comparisons to find the right pattern in the text? So we don't necessarily need to find a match. So in that example I just said, our best case for all occurrences was finding no occurrences. There's no guarantee that any of these algorithms are necessarily going to find a match. In that case, brute force, its best case was finding a match immediately in one occurrence or finding no matches in all occurrences. Good question though. So we have this last occurrence table, and I'll show how to construct it, but let's see how we're going to implement this in the Boyer-Moore algorithm. And I will be doing an example of this using the visualization tool if you want to go ahead and get that ready, because it's just going to be a lot to write on this board. We're going to start kind of similarly to brute force with I at 0. We're starting at the beginning of our text, but instead of j starting at 0, j is going to start at m-1. That's the last character in our pattern. And this is because unlike brute force, which compares forward, Boyer-Moore is actually going to compare characters backwards. So it's going to start at the end of the pattern and move back to the beginning. You'll see why we do that. It's so that we can skip over these large sections of text like I talked about earlier. If we started from the beginning, we'd have to do kind of a lot more effort to make that work. If we get a character match, this is really just like brute force. We're just going to decrement j. Let's move to the next character in our pattern. That's because these matches don't really give us a lot of information. It's the mismatches where the magic happens. Now, when we mismatch, we're going to need to use our last occurrence table. So what we do is we take our last occurrence table, we look at the character in the text that we failed with, and we get a number back out. I'm going to call that number shift. Now that number could be -1 if that character isn't in our text. Isn't in our pattern, or it could be some index in our pattern. Then what I'm going to check is if shift is less than j, this means that we haven't yet passed that character in our pattern. We're going to push I forwards by j minus shift, and that's going to realign our text and pattern so that the character we mismatched with lines up in our pattern. And again, this will make a lot more sense. I'll kind of show what this looks like after we actually run through the algorithm. That way you can kind of see it before and after. I've got a question. In our homework, do we need to explicitly define an entry in our last occurrence table that maps to -1? No, and I will explain why on the next page. Great question. So this is going to push I forwards to fix the alignment, and then we just move j back to the end of our pattern. So Boyer-Moore always, every alignment, we just start from the end of our pattern and move backwards. If shift is greater than j, this means that we've already passed that point in our pattern. You can see if we tried to do I plus equals j minus shift, and shift was larger than j, this would move I backwards. And we never want to move I backwards in any of these algorithms, because that's kind of going back to things that we should have already checked. So we always want I to be moving forwards. So if this happens, we're just going to, just like brute force, shift over by 1. We increment I and reset j back to m-1. And when we get a complete match in Boyer-Moore, all we're going to do is increment I and reset j to m-1. That's because, as I mentioned earlier, Boyer-Moore gets information when we fail comparisons. So if we get a complete match, there's no information we got because we never failed any comparisons. So you just have to shift over by 1. Now, before we actually run through this algorithm, let's look at the last occurrence table. So, last occurrence table, as I mentioned, is just a hash map. So we can just instantiate a hash map that's going to map characters, those are what's going to be our keys, to integers, which are going to be the values. Now, to actually implement this, we can just loop through our pattern. So we start at index 0. Every time we encounter a character, we just add that character into the hash map with its current index as the value. So we start with the character s, so that's our key, and the value is its index, which is 0. Next we get to this h, and that's at index 1. This a at index 2, n at index 3, g at index 4. Then now we get to this h again. Now if you remember from your hash map homework, what did we do when we encountered a duplicate key when we tried to do a put operation in the hash map? Well, if we tried to put h with a value of 5, what we would do is, instead of adding a new entry, we would just replace the old value. So when I try to put 5 in, I'm not going to create a new entry. I'm just going to kind of cross out this 1 and replace it with its new index, which is a 5. And you can see that this is going to now give us the last occurrence of every character, because every time we encounter a new occurrence, it's going to replace the old value all the way through to the end. Likewise, this a is going to replace this 2 with a 6. And then I is going to be 7. So what about that -1? How we generally represent that when we write out a last occurrence table is we write a asterisk as one of the entries and put -1. Now in our code, we don't want to map every single character in Java to -1, because that would be really expensive and take a really long time to do. But hash maps have this really nice method called get or default. And what get or default does is it takes in a key and a default value. And what it will do is, if that key exists in your hash map, it will give you back the value. And if that key does not exist in your hash map, it will give you back whatever default value you passed in. So in Boyer-Moore, if you use get or default with whatever character you're trying to check, and -1 is your default value, then if that character isn't in your last occurrence table, it will give you back -1, which is exactly the behavior you want. So that's kind of the answer to that question earlier. You don't have to explicitly put this -1 in your hash map, but when you're getting things out of it, you can use this get or default method to accomplish that. Now, I'm going to go ahead and shift over to the visualization tool, run through an example of this, then I'll go back to the last slide and we'll look at the algorithm again now that we've actually seen it run, and we'll talk about the efficiency. So, I'll also give you guys a little bit to ask questions and for me to take a drink of water. Alright, so here's our example in the Vis tool with Boyer-Moore. We can see our text is right here. It's a lot, so I didn't want to write everything down. And our pattern's right here. We're going to construct the last occurrence table first. That's always the first step of Boyer-Moore, assuming your pattern is shorter than your text. So I can go ahead and step through this. You can see it's just going to, every time we encounter a character, add it to our last occurrence table. So this 2 is going to overwrite this 0 automatically. We don't need to do any extra work to do that. C goes in as a new index, A overwrites this, B overwrites that, then A is going to overwrite that. So this is our last occurrence table. A with 6, B with 5, C with 3. And everything else is just going to have that inherent -1 value, which we represent usually with an asterisk and a -1. So now let's start. We're going to align our pattern at the beginning of the text, and we're going to start comparing at the end of the pattern. It's this last A. So you can see our first alignment, and this is where our comparison is doing. So this isn't really going to show what all the I and J pointers look like. You can imagine that the I pointer is always here at the beginning of this alignment, and the J pointer is in this text. Right now here it's at the end. So these two A's are going to match together, so we decrement J backwards by 1. Then these are going to mismatch. So we take this C, and we're going to look up in our last occurrence table, and it's going to give us the value of 3. That's our shift value. And if you remember back from what we talked about the algorithm, we're going to compare that shift value to J. Right now, if we calculate J, it's 0, 1, 2, 3, 4, 5. So J is 5, and shift is 3. Since shift is less than J, we can push I forward in order to align this C with this C in our pattern. That's the whole point of what this math is doing. It's just saying, okay, I mismatched with a C. I know a C exists in my pattern, so I'm going to align them together. And you can see now the two C's are aligned together. I've moved my I forward by 2. You can see that that was shift, which was J, which was 5, minus shift, which was 3. That's where this math came from. And now these C's are aligned together. So we can start doing matches. These two A's match together. Now we encounter this D. You'll note that D does not exist in our pattern at all. We did this last occurrence table. We can check an O of 1 time. It's not in our pattern. It's going to give us back -1. So what we want to do is we want to skip every alignment where this pattern includes this D at all, because none of them can possibly be correct, because D isn't anywhere in our pattern. And that math I talked about before works for this case with -1. That's kind of where these numbers come from, that if we do J minus shift, which is J plus 1 here, that's going to push everything past to here. So you'll see we've completely skipped over this D, and now we're aligned right here. We're going to mismatch with this B, and since we look at our last occurrence table, and that's going to tell us to align this B, this last B, with it right there. Now we start matching again. The A matches, the B matches, A matches, and now we get to this B. So our last occurrence table says that our last occurrence of B is right here. If we wanted to align this B with this B, we'd have to move our entire pattern backwards so that this B would be here, etc. But we never want to move our pattern backwards. That's kind of goes against the whole point of what we're trying to do. So this is going to be a case where shift, which is 5, is greater than J, which in this case is right at 3 right now. So when this happens, we just shift our pattern by 1 and start again. Just like this. Now we encounter this C. We're going to align our final C with it right there. You can see they're lined up. And then now we're going to do all these comparisons. This is where we're going to find our successful match. And because we found a full match, we don't have any extra information to do anything more, so we're just going to shift our pattern forward by 1. We get this mismatch here on the first character. That's going to try to line this B up with this B right here, but you'll see that pushes the A past the length of our text. So after we get this mismatch, we're going to be done because there's no more possible alignments in our text. So I'll give you guys a bit to ask questions about this example, and then I'll go back to the board. We'll look at the algorithm again. I'll talk a little bit about the efficiency. All right, I'm not seeing any questions, so I think we're going to go ahead and go back to the board. So this is the algorithm we talked about. Let's take a look at it again now that we've actually seen what everything looks like. We start with our initial alignment. It's the beginning of the text, end of our pattern. If we match, we just move on to the next character, which in Boyer-Moore is going backwards. When we get a mismatch, we get this value from our last occurrence table. If that value would cause us to shift our pattern forwards, then we shift our pattern forward so that those characters align. That's where this math comes from. And then we just start at the end of the pattern again. Else, this is what would happen if we tried to shift our pattern backwards. We're just going to move forward by 1. That's I++, and we reset j. And when we get a complete match, we just move our pattern forward by 1. I just saw a question. Would we just end when A is pushed past, or do we still need to make that last comparison? So you make the mismatch between A and B, but as soon as A is pushed past, you're done. There's nothing to compare it to. What is the purpose of having -1 as the value for a character that is not found? That is just how the math works out. So if you think about, if we mismatch at the very first character, that's when j is equal to pattern.length -1. Then when shift is -1, we get I plus equals m-1 plus 1, which is just I plus equals m. And I plus equals m just moves our entire pattern just past that index. So it's -1 mostly just because that's how the math ends up working out, to shift our entire pattern past that. I encourage you to play around with the math a little bit, see exactly how the numbers work out in all these shifts. A question about the brute force algorithm efficiency. Can I explain the best case O of m? So if we're looking for a single occurrence of our pattern and we encounter that occurrence on at the very beginning at index 0, then the only comparisons we have to do is we compare every character in the pattern, it matches, and because we found a complete match, we're done. And since the pattern is length m, it's just one O of m loop, and we're all done. Good questions. All right, now let's talk about the efficiency of Boyer-Moore. So you'll notice I have something interesting written here. I have no single average case. And that's because Boyer-Moore, as you'll see, can kind of perform vastly differently depending on your text and your pattern. So there's not really any one single average case that you can use for Boyer-Moore. It's never something that we're going to ask about. It's not something you need to worry about. There isn't really a single average case pattern in text that exists. So it's not really fair to say that for Boyer-Moore. Brute force just isn't really a great algorithm, so it performs badly on most patterns in text, but Boyer-Moore can perform wildly differently. So let's start with our worst case, because that one's much easier to think about. If we have a text that's something like all A's, ooh, this marker is not having a good time. So if this is our text, all A's, and our pattern is something like B, A, then what's going to happen is we compare all of these characters, they all match, up until this last character, which mismatches. Now B isn't anywhere in our text, but we don't know that. Our last occurrence table only gives us the list of characters in our pattern. So all we see is this A here. We can't align these two A's together, so we have to shift over by 1 and start the whole process over. And that's going to be just like brute force. So in the worst case, Boyer-Moore just is going to devolve into brute force and be an O of mn algorithm. There it goes. That's m times n, just like brute force. What about the best case? The best case, ooh, people are saying the stream is down. It is still working for me, and I'm not getting any frame drops. So hopefully it is not down for everyone. And yeah, other people are saying it's fine for them. Cool. So in our best case, this is going to be where we get to use that -1 case a lot in Boyer-Moore. So this is, say we have the same text of A, but our pattern this time is B, 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 B. What happens here? Let's give myself another A to work with. Well, I would check with this first B. It mismatches. And now I see that A, the character I mismatched with, isn't anywhere in my pattern. So I shift completely past it to this alignment. And this, I'm going to do the exact same thing again. I mismatch this character and I shift completely past it. And after just 2 comparisons, count them, 2. We're done. So that's really fast for Boyer-Moore. And how fast exactly that can be is going to be the length of our text divided by the length of our pattern, because we skipped over length of our pattern distance every time with one of these skips. So that's where we get n divided by m. But we have to remember, the first thing we do in Boyer-Moore is we loop over the length of our text, the length over our pattern once, and that is O of m time. It's not nothing like it was for brute force. So we have to add this plus m, and that is building last occurrence table. Now, this is for all occurrences, I want to stress. If you're looking for just the first occurrence, it's going to be just like brute force. It's one occurrence. Just like brute force, if we find our first match on the very first alignment, we're automatically done. But this is the kind of case we care about more, because it's very often we're looking for all occurrences. And having a division in your big O is a really good thing. Like we've seen things like with powers and squares. Maybe you've heard about like exponential big O's. This is something that has division, and you might think that's really good, and you would be right. This is a really good runtime to have. Boyer-Moore generally runs very fast, and that's why it's commonly used in a lot of tools. Like if you're familiar with like Linux and you've used like grep as a string searching thing before, I believe grep does use Boyer-Moore. So there's your bit of trivia. Another bit of trivia is the former dean of the College of Computing, Zvi Galil, actually like made some optimizations to brute force. It's obviously nothing you need to implement on your homework, but I believe the extension resources folder on Canvas has a link to his paper about it. So if you're curious, read up on that. See a question. So because the best case of Boyer-Moore has like big jumps, that's why it said Boyer-Moore is good for patterns with small alphabets and texts with larger alphabet than the pattern. Yes, that is a good summary. I'll talk about that more later after we've talked about KMP, which kind of works differently. But it's very obvious that if we get to do those jump cases a lot, Boyer-Moore is going to be a good algorithm, and that's some good insight. So if there's no other questions about Boyer-Moore, I'm going to go ahead and move on to KMP. We've got about 20-ish minutes left, so hopefully that should be enough time. Alright, the last algorithm we're going to talk about today is KMP, which stands for Knuth Morris Pratt. It's the last algorithm on your homework that you need to worry about. And unlike Boyer-Moore, KMP is an algorithm that's going to get information from character matches. So Boyer-Moore got to make all these big shifts because we mismatched at good points. But KMP is going to gather information as you make matches, and then when you make a mismatch, it will use that information to make intelligent shifts. How it does that is it's going to utilize prefix-suffix matches in the pattern. So that means that we have text in the beginning of our pattern that appears elsewhere too. So maybe in the middle, maybe at the end, but we have some kind of repetition going on. And a general rule of thumb for KMP that you can follow is once you have matched a character in the text, not just compared, you have to actually match it. We never compare that character again. So if we look at, I don't necessarily want to spend too long on the other slide because people are probably still writing this, but really quickly, you can see this character right here, we matched this H with something in our pattern, but then right here we compared this character again. KMP will never do that. After we made this comparison, KMP will never check this character again. And you can think about that because we do pre-processing on our pattern, we know what all of the characters in our pattern are. So if I match with index 2 of my pattern, and index 2 of my pattern is an H, then I know that character in the text is an H, and I should never try to compare it with anything in my pattern that isn't an H. That's kind of the logic. You'll see how that works. How we specifically implement that is something called a failure table. What the failure table represents is the nth index of the failure table contains the length of the longest prefix that is also a suffix of the first n characters of the pattern, which means we take our pattern, we chop off any characters after the nth spot, and we look for prefix-suffix matches. Now, what do I mean by prefix-suffix? I wrote out a couple of examples. So here we have ABCAB, and my prefix-suffix match is this length 2 AB that appears at the beginning and the end. So the longest prefix-suffix is length 2. An important note is that these prefix-suffixes need to be exact matches. So it's not mirrors, which a lot of people tend to get tripped up on. So this ABBA, the longest prefix-suffix match I have is only length 1. It's only this A. Because this AB is flipped over here, it's not a prefix-suffix. If it was ABAB, then we'd have length 2. Another note about prefix-suffixes is that they can overlap. Another question. If more precise, would it be O of m plus m, taking time complexity to build the last occurrence table? Yes, but also, as the question says, that's still O of m, because we drop, that's just 2m, and we drop those multiplicative constants. So, another thing about these prefix suffixes is that they are allowed to overlap. So here, my little text, my little pattern is ABABA, and I have a length 3 prefix suffix match of this first ABA and this last ABA. That middle A is shared between them, and that's important. Another really important thing is that the prefix suffix can't just be the entire pattern, because then everything would have its entire length be a prefix suffix match. So even if my pattern is just AAAA, 4 A's, the longest prefix suffix match is only length 3. It's only these first 3 characters with the last 3. I'm not allowed to include the entire thing, because otherwise that would trivialize the whole point. So it's not that bad to just kind of look at these texts and figure out how long these prefix suffix matches are, but how do we actually determine that in code? What's the algorithm we use to build this failure table? And that is going to be the next slide. So this is our failure table algorithm, some basic pseudocode for it. I'll give you guys a little bit of time to write that before I start working through it. Some notes. P is kind of the spot in my pattern. So P of I means the character in my pattern at index I, and F is my failure table. So it means failure table at index J. Obviously our pattern is stored as a string, but failure table is just going to be a normal array of integers. So the last occurrence table was a hash map. The failure table is just an array of integers. So let's look at what this failure table algorithm says. So we start with I and J pointers. I starts at 0, J starts at 1. Kind of an optional step you can include here is you can include setting the very beginning of our failure table to 0. So you can do f of 0 equals 0. But if you remember integer arrays, all of the values default to 0. So this is actually an optional step. And this step tends to actually trip a lot of people up when they're trying to build the failure table for a length 0 pattern, because this will give you an index out of bounds error. I didn't mention this yet. I think the failure table is going to need to be exactly as long as our pattern. So then we're going to loop until J has gone past the length of our pattern, so until J is somewhere out of bounds. We're going to compare index I and index J of our pattern. If they match, we're going to fill in failure table at J with I plus 1. Then we're going to just move I and J forwards by 1. Kind of get on to the next character. If they don't match, we're going to look at if I is 0 or not. If I is not 0, we're going to use our failure table to push it back. It's I equals f of I minus 1. That's going to push our I back, because it's impossible for any spot in the failure table to hold a value larger than its index, because we can't include the entire prefix suffix as a match. If we did, that could potentially cause infinite loops here. Then, otherwise, if I is at 0, there's nowhere for us to move it back. We're just going to put a 0 where J is and move J forwards by 1. Again, we don't really need this f of J equals 0 because they default to 0. I have a question. Why is the following needed in the failure table pseudocode? It's this line right here they're talking about. You will see, I will give an example. It does come up in this pattern, so you'll see when I run through the example, I'll pay special attention to when this line happens. But if we don't include this line, if we always set it to 0 and kind of reset back, we are going to miss some potential prefix suffixes. So let's start running through this algorithm. This is what I needed those I and j pointers before. So first thing, we have a 0 filled in at the beginning because length 1, we can't have a prefix-suffix match be the entire string, but that's the only character here. So there's no prefix-suffix matches we can have. We set our I and j, and we start comparing them. In this case, I and j don't match. It's an A and a B, and I is currently at 0, which means that we're in this case right here. We fill in a 0 in our failure table and move j forwards by 1. Now we have a case where they do match. So my algorithm says f of j equals I plus 1. I is at 0, so I plus 1 is 1. And then I move I and j both forwards by 1. Now, just as a recap from what I talked about in the last slide, if we ignore the rest of our string and just look at this ABA, you see that length 1 prefix-suffix match. This A matches with this A. And that's what that 1 represents. We move our I and j forward. Here we get a mismatch. And I mismatched when I is not equal to 0. So I do I equals f of I minus 1. Since I is 1, I minus 1 is 0, and f of 0 is 0, so I reset I back to 0. Note, I don't move j here. I just keep j where it is and move I backwards. And now I compare this character again with what my I is at right now. And here I find a match. I'm going to put a 1 here, because that's I plus 1, and move it forwards. Now note, if I, instead of moving I backwards and keeping j, if I instead had just shifted everything forward, I would have missed that length 1 prefix-suffix right there. So it's very important to not forget that. I do this comparison. It's a success. I plus 1 is 2. So I put a 2 right there, and I'm going to increment I and j. They match again. So I put a 3 there. Increment I and j. This is another case where this line is going to matter a lot. I get a mismatch, and I is not at 0. So I'm here. I equals f of I minus 1. If we look, I minus 1 is 2, and f of I minus 1 is 1. So I reset I back to 1. Not 0, only back to 1. And then I compare these characters again, and I find a match. And since I is 1, that means I put a 2 here. If I had just moved I back to 0 automatically, if I didn't have this case right here, I would miss this length 2 prefix-suffix match of this AB and this AB. So it's very important to not forget this step in your code. But I did get a match, so I move I and j forward. I get another match. Move I and j forward. A general rule, if you're just like diagramming this and not necessarily running through the algorithm, if you ever encounter a character that's not anywhere else in your pattern, this is always going to be a 0, but we'll run through with the algorithm. We mismatch, I equals f of I minus 1. That's going to reset I back to 1. Mismatches again, I equals f of I minus 1 is going to reset I back to 0. It mismatches a third time, but now I is at 0, so we just put a 0 here and increment j. J has gone past our pattern, so this is our failure table. If there are any questions about that, post them now. Otherwise, I'm going to go ahead and move on to the actual KMP algorithm. I'll show you what the algorithm looks like. We'll run it through in the visualization tool, talk a little bit about the efficiency and some of the comparisons between Boyer-Moore and KMP, and then we will finish up this recitation. All right, let's get back to the algorithm because I don't see any questions. Also, yeah, it seems like basically every service just went down. Blue Jeans, Microsoft Stream, Kaltura, everything just went down. So Twitch was kind of our only backup because people were out of options. But this works. We've done it before. It's nothing new to us. Let's talk about the algorithm. Same things I described for the other steps. We have our start condition, I equals 0 and j equals 0. Kmp, just like brute force, is going to start from the beginning of the pattern. Boyer-Moore is really the only weird one that starts from the end. If we get a character match, we're going to move j forwards by 1, kind of go on to the next character, and then the mismatch is where we actually use the failure table. If j is at 0, if we mismatch on the first character in our pattern, then we haven't gained any information. Remember, we gain information off of these matches. It's kind of like building potential energy. And if we mismatch at the beginning, we haven't gained anything yet, so we just shift by 1. But if we've made those matches, then we can use our failure table. So what this is going to be is we're going to push I forwards by j minus f of j minus 1. Now, j minus 1 is the last successful index we matched at. And we're going to use that value to realign our pattern. And again, I'll go through this a little bit again after we actually run through everything. But after we move I forwards, we're then going to reset j to just be f of j minus 1. A very important distinction. In the failure table algorithm, we did I equals f of I minus 1, but in KMP, we do j equals f of j minus 1. It's a very important distinction. As a note here, the value of I plus j, remember that's the character in the text we're comparing at, that has stayed the same after we did this. If you add these two together, you get I plus j back, because this is I plus j minus f of j minus 1. If we add f of j minus 1 to that, we just get I plus j. So you'll see we continue at the same character in the text we were already at. We just move where we are in our pattern, and we move where the actual alignment happens. When we get a complete match in KMP, this is very much unlike Boyer-Moore. In Boyer-Moore, we just did a shift by 1. But in KMP, remember, we've gained so much information through this complete match. What we can do is we treat it like we mismatched at index m. So we mismatched at the index past the end of our pattern. So this I wrote out, it's just this filled in with m. So if we treat j as m, that's m minus f of m minus 1, and j equals f of m minus 1. That's if we're going to continue looking for more matches. So we have this algorithm. Let's go ahead and pass it over to the visualization tool and see what it looks like in practice. So this is our KMP example. It is a slightly different text, so I'll give you guys a little bit to write that down as I run through the failure table, but it is the same pattern as last time. Let's go ahead and run the failure table algorithm. I'm going to go a little faster because you already saw how that worked. We're going to not match there. Here we have a prefix suffix of 1, 0 there, and then we're going to have 1, 2, and 3 respectively with the beginning of this. And that's our failure table. So now, when we start in the text, just like with brute force and Boyer-Moore, we start aligned at the very beginning, comparing at the index 0. Now we start comparing. Every time we get a match, we're just going to shift j forward by 1. And it's going to give us 3 successful comparisons. Now, here we get a mismatch. So what we're going to do is we look at the failure table of j minus 1. That's this a right here, and you see that has a value of 1. And what that says is the last character we matched also appeared at the beginning of our pattern. There was a length 1 prefix suffix. So we can line this a up with this a right here because we know it's there. You'll notice I plus j hasn't moved. So this column didn't change. We're still comparing with the same character in our text, and now it's a different character in our pattern. You'll also notice that this A is highlighted in yellow. We did not do a comparison with this A and this A. We know it matches because of our failure table, but we didn't do an explicit comparison. We're just going to start from this B. We're going to get matches. And then here we get a mismatch with this D. We look at our failure table, and it says to align, what it essentially says is align index 1 of my pattern with the current index of my text. So if we look, index 1 of our pattern is now lined up in this column. That's what the math works out to. We compare again, we get a mismatch, and this failure table says align index 0 of my pattern with where I am in my text. So we do that. Now we mismatch on index 0, and the only thing to do is shift forward by 1. We're going to start comparing again. We get a mismatch. We're going to line up index 1 of our pattern with where we are in our text. Or sorry, with where we are in our text. You'll notice that lines these A's up. We don't compare this A again. We get another mismatch. That's going to line up index 0 of our pattern with where we are. We do all of these comparisons. Now we get a complete match. So what we're going to do is we're going to shift based on this last value in our failure table. And we're going to treat it like we failed on this column, this C right here. So by the same logic I've been saying earlier, we're going to line up index 3 of our pattern with this column right here with this C. And you'll see that's 0, 1, 2, 3, index 3 of our pattern right here. And we start comparing again. We don't compare any of these 3 letters. And we get another match, and that's the algorithm complete. If we would try to do a shift past this, we obviously extend past the length of our text and we're done. Now, again, just to stress the thing I mentioned at the very beginning, if you look at all of these columns, every column contains at most 1 green box. Once we matched a character in our text, we never compared that character again. You'll see here, it was a yellow thing. That means we skipped the comparison in all of these cases. So once we matched a character, we never compared it again. So I'm going to leave it on this for a little bit, then move back to the algorithm. We'll talk about the efficiency, and then we'll talk about kind of the differences between Boyer-Moore and KMP. Running a little low on time, though. So submit your questions if you have them. I will answer them while I'm talking about efficiency. So, what is our best case? What is our worst case? Well, just like Boyer-Moore and brute force, if I'm only looking for one occurrence of my pattern, then I can do a best case of O of M. Because I just match that pattern and that's it. But if I'm looking for all occurrences, then my best case is if I mismatch on that very first character every time and just kind of do all of those shifts by 1. And that's going to be, I have to use O of M time to construct my failure table, and then O of N time to loop through the text. And that's going to give me O of M plus N. Now, for our worst case, this is one thing where KMP is actually really nice. Because we never recompare characters that we've already matched, we're only ever going to compare any given character in our text a constant number of times. You'll notice that the characters that we compared a lot were because we got a lot of matches beforehand. If we didn't have matches, we would have just shifted past it. So, in the worst case, we actually have the time it takes to construct the failure table plus a constant amount of loop through our text. So even in the worst case, it's only O of M plus N, which is pretty good for KMP. That's a pretty good runtime to have. And if you can imagine, since we have a best and worst case of O of M plus N, that means we can have our average case is just going to be O of M plus N as well. Because in general, we don't have to do that many comparisons of the same character over and over again. We just kind of get to keep doing these shifts forward. So these are KMP's efficiencies. You'll see it has a much better worst case than something like Boyer-Moore, but the best case isn't quite as nice. There's no division in there. So now let's talk a little bit about the differences between these algorithms as last couple questions come in. So, as was mentioned earlier, Boyer-Moore is a really nice algorithm when you have a when there's not a lot of overlap between the letters that appear in your pattern and the letters that appear in your text. That means we have a large alphabet of characters. Could I re-explain why the worst case of KMP is O of M plus N? So it's kind of hard to explain really well in a short amount of time, but basically what happens, I'm going to go back to the Viz tool. What happens is we don't compare, even when we get mismatches, we don't compare that same character a lot. You see, we compared the same character 3 times here, but that was because we had a lot of matches beforehand. So we're not ever going to end up comparing same characters in our text like m times each. Because we only, after we get a match, we move past it. And if we get mismatches, we move back to the beginning of our pattern, and that time takes at most the number of successful matches we had beforehand. I'm not going to be able to write out all of the math right now, but we're not doing more than a constant number of comparisons relative to the length of our pattern and the number of matches we've had. So that's where that O of m plus n comes from. It's a little bit hard to explain right now. I encourage you to kind of mess around with it on your own and see that even in the worst cases you can think of, you don't really get that bad. So, back to the comparison. When we have this little overlap between our pattern and text, that means we get to use that skip case a lot. That's where we kind of get that division, that n over m in our efficiency. And if we have a large alphabet, this tends to happen. If you think of like the ASCII character set, there's 26 lowercase letters, 26 uppercase letters, 10 digits, spaces, periods, commas. That's a really large alphabet. So Boyer-Moore does really well in cases like that, where we have a lot of characters. Do I happen to know if Java's string.contains method uses any of these? Could I go back to the efficiency slide once I'm done? I can, but I'm probably going to have to cut the stream after a little bit. You will be able to rewatch these, obviously, and look at them. If I had to guess, it uses some variant of Boyer-Moore, because that's common, or Rabin-Karp, which is the algorithm we didn't talk about today. I'm sure that's something that's on the internet that you could look up. Sorry, I didn't really know that in advance. KMP, by comparison, Boyer-Moore worked for large alphabets. KMP is going to work well for small alphabets. And that's because with small alphabets, we get a large amount of overlap. There's a good chance that we have overlap in our pattern. If I'm only dealing with a couple possible characters, then there's a really good chance that characters repeat, or I have patterns that repeat. So what's a situation where I have a lot of repeated characters? Well, what if I'm doing DNA sequencing? That's something where I only have an alphabet of size 4. I have A, C, T, and G. Someone's really mad I said them in that order. But I only have a couple characters, and I'm going to have a lot of prefixes and suffixes that match up. And that works very well for KMP and very poorly for Boyer-Moore. Another good thing for KMP is that thing I mentioned earlier, that we only ever kind of move forwards with the text. We never go backwards at all. We never compare another character again after we've matched it. It's really good if we have a stream of text that we're not able to store on a disk because it's just too large. We're looking through a really long thing of data. So that's really nice for KMP versus Boyer-Moore. You see we have to move like forwards and backwards a lot as we're going. KMP only moves forwards. So if we're looking at a stream of text, KMP is really good. I'm going to really quickly go back to the other slides and keep them up for a couple seconds each. You can screenshot them if it helps, or just look at the video afterwards. Then I'm going to end the stream because I am kind of out of time. You can see this is the KMP efficiencies down here. Boyer-Moore are right over here. Hopefully you can get that down. It was a great recitation. Sorry we went a little over. Had a lot to cover. Wanted to make sure I was kind of detailed through everything. You'll be able to watch these videos on Twitch. They will be uploaded to Canvas on the media gallery as soon as I can. Hopefully tonight. I can't really make any guarantees, especially because if systems are down, who knows. But I will have these up as soon as possible. Thank you guys for tuning in. It was a great stream. Landon will be here very shortly with the 6 p.m. recitation stream, and have a good night.